Hello, everyone. Imagine you are a manager of a busy restaurant. Customers keep walking in. Some just want a coffee, others order full meals that take a longer to prepare. To keep everyone happy, you can't just serve in an order they arrive. You need a smart way to handle both quick and long orders. That's exactly what an operating system does when it handles multiple processes. It needs to schedule them in a way that keeps the system fast, responsive, and fair. Today, I, Ashwini Chaurasia, Harsh, and Shreyans will be talking about one of the most dynamic and intelligent CPU scheduling algorithms, the Multi-Level Feedback Queue, or MLFQ. So, we are the team Control Plus Q. Multi-level feedback queue is a scheduling algorithm using multiple queues with different priority levels. Processes move between queues depending on the CPU burst, waiting times, and how much CPU time they use. This idea is to favor short, interactive jobs but still allow long CPU bound ones to execute without starvation. MLFQ follows four main rules. Rule 1: every new process starts in the highest priority queue for fast initial process. Rule 2: if a process uses its full time slice, it's considered CPU bound and is demoted to a lower queue. To avoid starvation, processes waiting too long are promoted back up. This is called aging. Rule 4: a higher priority process can preempt a lower one, ensuring urgent tasks run quickly. MLFQ uses multiple queues, each with its own priority and time quantum. For example, Q0 is the highest priority, then Q1, and so on. The scheduler always runs a process from the highest non-empty queue. Within each queue, round-robin scheduling is used for fairness. As we move to the lower queues, that time quantum increases, say 4 milliseconds, 8 milliseconds, 16 milliseconds, etc. This helps interactive job finish fast and reduces overhead for longer jobs. In short, MLFQ adjusts priority dynamically to stay responsive and efficient.
Hello, I'm Harsh and I'll explain the code implementation of multi-level feedback queue scheduling algorithm in C. First, we include the standard libraries stdio.h and stdlib.h. Then we define two constants, max processes for the number of processes and max queues for the total queues used in our MLFQ system. Next, we create a process structure which stores details of each process like its process ID, arrival time, burst time, remaining time, waiting time, turnaround time, response time, and which queue it currently belongs to. We also have a queue structure which represents each level of the feedback queue. Each queue has its own time quantum and uses a simple array to store process IDs waiting inside it. After that, we define some helper functions like initQ, which initializes each queue and sets its time quantum, and QNDQ, which are used to add and remove processes from a queue. IsEmpty checks if a queue is empty. All done checks if all processes have been executed. Inside the main function, we first take the number of processes from the user and then input each process's arrival time and burst time. The remaining burst time is initialized equal to the burst time. We then initialize three queues with different time quantums. Q1 with 4 units, Q2 with 8 units, and Q3 with 12 units. The idea is higher queues get shorter quantums and higher priority. The main logic runs inside a while loop until all processes are completed. At each time step, the CPU picks the first available process from the highest priority non-empty queue. The process executes for either the queue's time quantum or until it finishes, whichever comes first. If it finishes, we calculate all its metrics, turnaround time, waiting time, and response time. If it doesn't finish, we demote it to the next lower queue for fair scheduling. During the execution, if new processes arrive, they are automatically added to the highest queue. This ensures newly arrived short jobs get CPU attention quickly. Once all processes are done, the program prints a summary table showing each process's details. Start time, finish time, turnaround time, waiting time, and response time. Finally, it calculates and prints the average waiting time, average turnaround time, and average response time for the system.
So, hello everyone. In this slide, we'll be discussing the key advantages of MLFQ scheduling. This scheduling is effective because it balances responsiveness, fairness, and adaptability. It gives high responsiveness by quickly handling short and interactive tasks like IO processes. It adapts priorities automatically. Processes that wait often get higher priorities, while CPU heavy processes are adjusted down. It prevents starvation through aging, gradually promoting long waiting processes. And it's flexible, means we can tune the number of queues, time quanta, and promotion rules to optimize the performance. In the next slide, the disadvantages and implementation challenges. So, MLFQ has some challenges. It's complex to implement due to multiple queues and priority rules. Performance depends on the proper tuning of time quanta and aging parameters. It adds overhead because the system must constantly monitor and adjust processes. Without careful aging policies, low priority processes can still starve under heavy load. The final slide, the MLFQ summary, the adaptive scheduling solution. So, in the summary, it is an adaptive scheduler combining strengths of multiple algorithms. It responds to the short task, fair through aging, and adaptable as priorities change based on the behavior. It also improves efficiency with longer time quanta for CPU bound tasks. This makes MLFQ a foundation for modern OS like Unix, Linux, and Windows, effectively managing diverse workloads.
Thank you everyone for listening. I really appreciate your time and I hope you enjoyed our presentation.